Can you see my screen?
Yes, sir.
Okay, now let's start the part B. I said that in part A we read about the electrical and electronics instrument. In part B we'll read some other physical instrument which is not measuring the electrical quantity. So the biggest and the important type of measurement is the measurement of displacement. Okay. So what do you mean by the measurement of displacement? Okay. So measurement of displacement means that when you want to measure the length or the displacement, then this type of measurement will come. So it is not only the measurement of displacement. When you see or measurement the displacement or x, and that is related to many things. From that you can measure many things. For example, if you can measure the displacement, you can measure the position, you can measure the velocity, you can measure the acceleration also, and also strain measurement also will come inside it. So this displacement sensor, when you measure the displacement, we call it the displacement sensor. So we'll read various sensors in displacement sensor, and we discuss many things, and few other displacement sensor also we will overlook. And you will see that there are, they have also mentioned in the book Sahani, but a few important displacement sensor only you will see, because other sensors we cannot cover everything. Okay, so in this section what basically we'll read, initially we'll read with the displacement sensor, for example potentiometer, then we'll go to other things like LVDT. Okay, and then we'll go to seismic sensor measurement, that is also a type of displacement sensor. Then we'll go to the strain measurement, we'll go to the encoder type of instrument. Okay, we'll go to the piezoelectric type of transducer. All those things we'll read. Okay, so this chapter is quite big. So now let's come to the first point, the measurement of displacement with the help of potentiometer. So in the figure which is shown in the slide, you see that all the things are the potentiometer. Okay, so let's see that the topmost left hand side figure, which is a potentiometer, where the input voltage is EEX, and the potentiometer there are various X. You see that X is the displacement, so output is Xi. So if you look at the uh, figure, this figure, topmost left hand figure, so it is basically a transitional potentiometer, simple potentiometer. There a DC voltage of EEX is applied, and the slider moves on the resistance, and slider displacement is Xi, and output is E0. So output you can measure with the help of voltmeter. So you get output voltage, and displacement is the input. So output will be proportional to the Xi. So based on the voltage measurement, you can tell how much displacement it is. Very simple instrument. Okay. So if you plot this Xi versus E0, how the plot will look like. So here your input is Xi, which is a slider displacement. Output is E0, which is a voltmeter. Now we are assuming that voltmeter is ideal voltmeter, no current passing through it, and its resistance is infinite. There is no loading effect. So if we assume such ideal voltmeter, you know that the voltage output will be proportional to the input Xi. You see the straight line graph. In x-axis we plot the Xi. In y-axis we plot the theta, or we plot the E0. So as the Xi will vary, E0 will increase, and that is very linearly increasing. Okay, so it is a linear instrument, provided we assume that the voltmeter what we are using to measure the output voltage has infinite resistance and no current is passing through it, and so there is no loading effect. So this is for the ideal situation. Now let's come the second figure, this one. This is also potentiometer, but this is actually the rotational potentiometer. Okay. So here you see that the input voltage is X again, and that is going through through the resistance, which is arranged in a circular fashion. So resistance is arranged in a circular fashion, and it is going to the resistance, this EEX DC voltage. Now the slider is moving on the circle, and the output is again the potential difference. We are measuring one end of it is on the input voltage, another end of which is on the slider. So in translational potentiometer, slider can move on a line, and rotational potentiometer, slider will move on a circle, and that circle is made of resistance, and input voltage will be provided in the resistance, and the slider is connected with the output potentiometer. So again, this is a circuit of displacement measurement, and if you see um, and if you plot, you will see that the theta is the input and the output is E0. And again, if we assume that the output is output potentiometer, output voltmeter has infinite resistance, no loading effect will come. So theta versus E0 will be linear. So it will become a linear instrument. Okay. Just hold on for 1 minute. Okay. So now if you see the third figure, basically it is a kind of helix. So it consists of rotation as well as the translation. So this is kind of rheostat type of things you see. So it is rotated and then it goes. So what happens in this way, you can wound a long wire of resistance so that the resistance can be increased. So it is called a rotational but multi-turn. So what will happen? You see the theta I is the input here. When theta I is rotated, so what will happen? This long rod, it will rotate and keep on advancing. Okay, so the length of it is increased hugely. Okay, so resolution is increased. That is coming. I'm coming it later, not now. So for the timing, you see that this is a multi-turn resistance, and this can be used. So when you give that rotation theta I, the slider will rotate and move forward. Okay, kind of helix movement. So it will rotate and move forward on the wire, and you measure the E0, and from there you can calculate the theta I. So it is called the multi-turn potentiometer. So these are the three types of potentiometer you can see. So now if you see, if you plot it, when we assume that there is no loading effect, that means the potential E0, the voltmeter, what we are measuring to E0 has the infinite resistance and no current is passing through it. So what will happen? That input xi or theta I will be, output will be proportional to the input, which is xi or theta I. So this is all about the potentiometer, which is translational or rotational. And also last figure I show the multi-turn.
Now let's come to some calculation. So what we are saying? We are saying that if the E0, the voltmeter, has the infinite resistance, so there is no loading effect. So then simply E0 will be equals to EEX divided by capital R or capital L, which is the full length, which is constant, into Xi. So E0, EEX input is the constant, full length is the constant. So E0 will be proportional to Xi. It will be linear device, very simple. But in reality, it is not so simple because there is no meter which has infinite resistance. Resistance can be high, but it cannot be simply assumed that infinite. Okay. So we have to see that how loading effect come into play or can deteriorate it. So now for to do it, so we assume you see the figure on the left hand side. So what we assume? We assume that E0 has the resistance Rm, which is very high. So if E0 is the resistance Rm, so then what the circuit is becoming? Circuit is becoming a input voltage is applied. It is going to a resistance whose resistance is Rp, and you have a displacement slider whose displacement is Xi, and it has a displacement slider whose displacement is Xi, and it has a output E0 going through the meter whose meter resistance is not infinite, meter resistance is Rm. Okay. Now what will be the E0 by EX? E0 by EEX, what will be? This is your homework. You will calculate what will be the expression of E0 by EEX. I am writing the final expression. This is your homework to your exam also. But take it as a homework. I am not going to derive. It is very simple to derive. So E0 by EX will be 1 by Xi by Xt plus Rp by Rm into 1 minus Xi by Xt. Xt is the full length, Xi is the displacement which we want to measure. So this expression, you try to prove it. It is very simple. So from this expression, you can see if Rm goes to infinity, what will happen? Rp by Rm will be 0. So E0 by Ex will be Xt by Xi by Xt. So our E0 will be proportional to Xi. This one. When Rp by Rm equals to 0, that will happen when Rm tends to infinity. Then E0 by Ex will be Xi by Xt. So E0 will be proportional to Xi. That's it. But if Rp by Rm is not equals to 0, that means the meter is not ideal. Then how it will look like if we want to plot Xi by Xt versus E0? This is the plot. Okay. Xi by Xt versus E0. So we see that this plot, so if Rp by Rm is equals to 0, it will be straight line that we have seen. If Rp by Rm is not equals to 0, but it is something finite, then the plot will not be linear. So it will be a non-linear and it will be deep into it. Okay, although initial point and final point will be same, but it will be non-linear and it is going to be a kind of curve. So then you see, for in reality, our potentiometer instrument does not remain a linear instrument. Okay, so it dips, and so if we use the linear relationship, so you will be doing some mistake. So this is the thing. So now what we can do, how we can add one resistance R in. You see this figure. We can add one resistance R in equals to Rm. Okay. If we add this resistance again, your homework is to calculate what will be the R0 in presence of that. And if you calculate, you will see and plot. You will see with R in. Without R in, the figure will be like this, dipping. So always dipping from the straight line. If within R in, so it will little bit deep, go and then again come back. So if you include the resistance R in, the linearity of the instrument will be more. it will be less nonlinear. But without including of Rin, it will be more nonlinear. Okay. Now there is other aspect. So now tell me if you understand. So therefore, when no loading is present, the curve is perfectly straight line passing through the origin. But in practice, there will be potentiometer, their voltmeter will have some resistance. So Rm will not be infinity. And the equation shows that this equation E0 by Ex shows that a nonlinear relationship between Xi and E0 will exist. Thus, the derivation or thus the deviation from the nonlinearity is there, and as Rp by Rm increases, the curve will become more and more nonlinear. To avoid this also, we make another arrangement. We add another resistance Rin, which is equal to Rm. In such a cases, we see that the expression you have to derive, and from the expression you can see that it is still non-linear, but the linearity will improve. Non-linearity will be much less without Rin. So is it clear up to this? Tell me. So if it is clear, then we'll move. If you have any query, you can ask or write on the chat box. Okay, thank you. So it is clear to all of you. There are few aspects. Okay. So what I'm saying now that since E0 is directly proportional to Ex, suppose we take the ideal potentiometer. So E0 means output voltage is directly proportional to Ex, input voltage, whatever be the case. So it would seems possible to get any sensitivity. What is the meaning of sensitivity? So if your output voltage increases, then sensitivity will be more, because with some Xi you will get more output, sensitivity will be more. So now I can ask you that how the sensitivity of this instrument can be increased. So you can simply answer that the sensitivity of the instrument can be increased if we increase the input voltage EEX, because with the increased input voltage increasing, output voltage will also increase, and we will get the sensitivity whatever we desire. But the reality is not so, because suppose these are the all engineering aspect. So you try to think. Suppose we are increasing EEX to increase the sensitivity. But what will happen? EEX means more power or more DC voltage. Okay. But if we increase the DC voltage, can this potentiometer take any input voltage of any magnitude? No, because the potentiometer has some power rating. Related to that, heat dissipation is depending. So it cannot go beyond the power rating of the potentiometer. If it goes beyond the power rating of the potentiometer, the heat dissipation will be more and the potentiometer will be damaged or melt. So now if the heat dissipation is limited to P watt, let's say maximum heat dissipation which potentiometer can have is limited to P watt. Okay. So what will be the maximum excitation voltage EEX we can give? We can give maximum excitation voltage is square root of PRP. Square root of PRP, where RP is the resistance, this one, a potentiometer, and P is the power rating. So that much maximum power of maximum voltage of EEX we can give. Thus, if we give thus a low value of RP, if we have a low value of RP, then the excitation voltage EEX must be limited, small, and the sensitivity will be small. So high value of RP is desirable, right? So from this discussion, what we get that high value of RP is desirable, because we can make power rating will be more, we can give more input voltage, sensitivity will increase. Again, you see that the good linearity, what we need, Rp by Rm will be equals to 0. So for getting more sensitivity, if we increase Rp, what will happen? Rp by Rm will be increasing because we are Rm is fixed, Rp is increasing. So if it is increasing, the output will become more and more nonlinear. So if we try to increase the sensitivity, our output will become more nonlinear. So we cannot increase the sensitivity at any values because the output will become more and more nonlinear. So we have to keep the balance of it so that output becomes somewhat acceptable linear nonlinearity and the sensitivity is also kind of acceptable. Okay, so you cannot go anything very high. Sensitivity of very high sensitivity cannot be achieved because it is contradicting with the linearity. Okay, so we need to have a trade-off. Is that okay to all of you? Let me see whether is there any query, because this is important discussion. Okay, no query. Now let's discuss about the resolution. Okay, now let's discuss about the resolution. So this figure, you can see that construction of wire wound resistance element. So we have to have resistance, and the resistance element is generally constructed for linearity. There will be a bar and then you wound the wire, and for circular thing there will be a circular bar, you wound the wire around it. So in this way you can make a construction of wire wound resistance element. Now you see, try to zoom this one, and you have a wiper moving on this resistance. So if you have a wiper moving on this resistance, you come to this figure. What is happening? You have the all wound. So you might have the slider on this resistance wire or this resistance wire or this resistance wire. Okay, inside slider you don't have. So if when it is this and this, the resistance is not continuous, there is one turn of wire is not traveled. So resistance of one full turn of wire is added with this to this and this to this and this to this and this to this. So resistance of wire, one full turn of wire is going to add, and the wiper will move on it. So you will not get the continuous resistance values because you are wounding this resistance on a bar and the wiper is going on the bar on a particular point on the resistance. So if you see that, what will be the R values, okay, as the displacement X. So when displacement is 0, there is no R, and then it moves, the R increases, and the next turn when it goes, the R increases with a jump. So the increase of R will not be continuous. So it will be discrete. So it's a step increase. So in resolution also, as the R increase of R is not continuous, so resolution also will be affected. So resolution of the potentiometer will be strongly influenced by the construction of the resistance. If you construct the resistance in such a way that wire wound, you have a wire resistance which is wound, and then your resolution will not be very high. But suppose you can ask, sir, so we don't need wire wound. I will take a straight wire as the, I will take a straight wire, only wire, one straight wire, and I will move the slider so that resistance will vary continuously. Very good. That is acceptable. But if you owned a wire on the owned a wire, then lot of wire you can compress and own so that resistance will be more. If you have a single wire, the resistance will be very, very less. So the total resistance will be very less. Okay. So to make that continuous thing is happening, but as the resistance or change of resistance is very less, so although the resolution will be high, then you might have a very long wire to travel the full resistance. So such a potentiometer are available, but is limited for the small resistance value. And for such potentiometer, you may have very large space, because a single wire having considerable resistance, you have to have very long wire, and your slider will move on the single wire, and you need very large space to accommodate that resistance when there is no wound. That is also one constraint. So you have to, so the key takeaway is, when you are going to maximize something, you may have realized that that is also limiting some other thing. So you need to have trade-off. For example, if you are trying to increase the sensitivity, you increase the input voltage, but that is going to limit it for the maximum power dissipation. Okay, and for that you have to have limit the input voltage. You cannot go whatever the sensitivity you want, and for that you also see that it is again the of good linearity, because rp by rm is going to increase. Okay, so if you want to low value of rp is allowed for that eex, then rp by rpm is going to increase, so your linearity is also going to affect it. Again, if you see the resolution, if you want, you need to have some resistance on the potentiometer, and you, for that space restriction, you won't it on around on an former or something. And then if your slider moves, then the change in resistance become decrease in step, not continuous, and that affects the resolution. Now, if you want to get good resolution, then you cannot wound it. Then you have a straight wire, and to cover to make a resistance with the straight wire, you need a very long space, and that is coming as a space constraint. So you cannot do it. So there are a lot of trade-off when you design one instrument, and that you have to think whenever you are going to maximize something, it might happen limiting some other thing. So all those things you have to consider in your mind. Now tell me, this is the end of the potentiometer. So dynamic characteristics, you know that if you have potentiometer is zeroth order instrument, that all of you answered in the, and if, but you have some loading effect, and then the linearity can be affected, that is fine. So but the instrument is in zeroth order. Okay, now you tell me if you have any query on the potentiometer.
So can you explain that again, that why we are not using a straight Y for increasing the resolution?
Yeah. Resolution you mean to say, na?
Yes, sir.
Okay. So suppose how we construct the potentiometer, you have to think about the construction. This figure I can make more like this. So you see, when you construct an potentiometer, we generally have an insulating cord, and on that the wire is wound, right? So wire is wound such a way that it is on the insulating cord. Now we have a wiper. You see this figure. Okay, I can also make it large. So the wiper is this, the wiper, and it will goes on the wire. So now take the contact point. So wiper will be either in this wire or the next wire. But when you are going to next wire, that means that this wire is making one round and coming to next point. But the wiper is not going through the wire, it is going to the next point. So the resistance of that one wound is not covered by the wire. So if you keep plotting the resistance versus the displacement, so one displacement means next wire, but the resistance is not continuously changing, it is changing in a discrete way, because the wiper is not covering the full wire. So what it is doing, it is going to the next wire, and one full circle or full wound of the wire, the resistance due to that is adding with it. So if we plot the resistance with the x, so the next displacement, what is going to happen, the resistance is increasing slightly, and the increase is not continuous. As the resistance increase in resistance is not continuous, then what is going to happen, resolution is going to affect it, because you are not going the output for this one wound, so resolution will be affected. So to make the resolution affected less or to make the resolution more, you can say that, sir, you don't wound on a insulating cord, you just take a straight wire and straight. So when wiper will go to straight wire, definitely that will not be discrete, it will be continuous because wiper is moving through the wire and all the point is connected. But suppose if you want to make 10 ohm resistance, so for that this insulating, if you wound it on an insulating cord, it will take very small space. But if you want to make the same resistance or same wire in a straight line, then you cannot wound it, and you take that wire out of the wound and make it straight. How big that wire will be? So that much space is required. So that is quite unrealistic. So what is happening? We are compromising for resolution to make it more compact or to so that less space is required. Is that fine?
Yes, understood. Thank you, sir.
Yeah. Okay, now the potentiometer is over. So you try to derive all those things. So what is your homework? What you will derive? So it may come to exam. You will derive the expression of it when Rm is present. It is not infinite. One thing. Second thing, you will plot it and you look. You can plot in MATLAB or Python, wherever you like, that expression when this xi by xt is varying. So you will see that how when the Rp by Rm is going to increase, how this plot is going to deviate from the straight line. The next homework is you include R in equals to Rn, and then you calculate the resultant output. Again, you plot it with the help of MATLAB or Python, and then you see how the linearity is increasing with the increase in Rin. So this will come in exam. Okay. So you please note it. So if I give that and then you say that, sir, you did not tell in class, so you don't tell it. Huh? So even this plotting, okay, or this coding, that can also come in exam. I can say that write a code in any language so that you, when you increase the value of xi, how the increase of output is going to happen, plot it. Okay, then you have to derive and you have to take this expression to your software, MATLAB or Python or whatever you like, and then you plot it. I want to see the plot. Okay, so that may come in exam also. So all those things are about the static characteristics, about dynamic characteristics. You know, this is a zeroth order instrument. So whatever input you will give, the output will follow directly. But E0 will follow directly. But if you want to measure it with a voltmeter, again you apply a voltmeter, and if that voltmeter is a second order instrument, your overall measurement will become a second order measurement system. Okay, do you understand that? Ideally, if you employ a voltmeter to measure the E0, then Xi by E0, if you take care of the voltage, voltmeter, dynamic characteristics, it will become second order. But ideally, if you have any output E0, which you are measuring, ideally, instantaneously, then your system will be zeroth order. Okay. Now let's come to the next instrument, strain gauge. Okay, strain gauge we can start next class. Okay, it is a quite big. Uh, okay, fine. Strain gauge we can start in the next class. It is already 50s. Okay, so tell me if you have any query in today's class. It's a long class we took. If you have any query, please tell me. Okay, so if you have no query, then maybe now you can leave or we can stop here. Again, we will be on Monday. Monday we have a class, so we'll come Monday and we'll start taking the classes. And now I am telling that the end same syllabus will be mid same plus after mid same full syllabus. Okay, so that you keep into mind. Mhm. So you keep on start reading the book. This potentiometer and strain gauge, everything you start reading from Doebelin, and you also try to see the examples and all those things from the Doebelin. Okay. Thank you. So now you can leave. So happy. Yes, Kollan is asking that coding part be an assignment. Yes, it is an assignment, but I don't need you to submit it. You do it on your own, home on your own. Because if why I don't need to submit it, because my experience is if I ask to submit the assignment, most of the students will blindly copy the assignment from others and submit it. So that is not going to be helpful anyway. So you solve it, okay? So it may come in exam or you solve it on your own. No need to submit. Okay. It will be homework. Is that fine? Okay. Okay. Thank you. Have a nice day. So now we end here. We'll meet on coming Monday.